Hi students, welcome to the session on basic and discrete time signals. Already I posted one video on some discrete time signals, basic discrete time signals. This is continuation, right? Let us start with sinusoidal signal, right? In discrete domain, right? Like we have a sinusoidal signal in continuous domain, we have sinusoidal signals in discrete domain also. So that is represented as x of n. It is represented only in discrete time. So that we can write as a cos omega n. Fine. So where omega is equal to 2 pi f, that is equal to 2 pi by n into m. F is equal to 1 by t. Sorry, 1 by n here. So f is equal to 1 by n, where n is a fundamental period. This and all we study in detail in the upcoming sessions. So m is the smallest integer, right? So m is smallest integer. So these things we will learn in the upcoming session, right? So omega is unit is radian per sample. The unit of omega is radian per sample. In continuous it is radian per second. Here it is radian per sample, right? So now how can we draw sine cos wave in discrete domain? You see it has to be like this. Cos is having maximum at 0, so it will be here 0. Then we know it is gradually reducing, right? Same thing. Fine. So here it is like this. Here again going like this. Okay, this is like this. Then it is coming, right? This is what you call cosine wave. You see, this is appearing like cosine, right? This is x of n is equal to a cos omega n. Similarly, we can draw x of n is equal to a sine omega n. All the parameters are same. How can we draw sine wave? We know how to draw. So this is what we have to draw, sine wave. Initially it is 0, right? Then we can go for this one. Then it is going again coming down, right? So this is what we know sine wave. Right? It is following the same track. So this is what sine wave, right, in discrete domain. Similarly, we have an exponential signal in discrete domain. Exponential signal, discrete, right? So that is represented as x of n is equal to a power n, right? Where n is greater than or equal to 0, right? So suppose, right, how can we draw this? Right, x-axis n, y-axis a power n, x of n. So you see, we assume that initially a is lying between 0 to 1, right? When a is 0 to 1, so let us assume it is, for example, a is 1 by 2, 0.5, 1 by 2 power n. So when n is equal to 0, 1 by 2 power 0, 1. So it is like this, sum up, right? Next, when n is equal to 1, 1 by 2 power 1, half, it will become half. When n is equal to 2, 1 by 2 power 2, 1 by 4. So it will become again part. So like that it will go, this is decaying. So this is what decreasing exponential. Fine? Okay. Now we assume that a is greater than 1. When a is greater than 1, let us assume 2. So 2 power n, right? So as usual you draw, when n is equal to 0, 2 power 0 is 1, right? So this is 1, n is equal to 0, this one. When n is equal to 1, it will be 2 power 1, 2. Let us go this 2. When n is equal to 2, it will go to 4. So it is increasing exponential. It is going to 4. Like that it will go up. So we can call this is increasing exponential. Right? This is what real exponential signal. Right now we go and learn a complex exponential in discrete domain. Complex exponential. Like we had a complex exponential in continuous domain. we have a complex exponential in discrete domain also. That is represented as x of n is equal to an e power j omega n. That you can write as a power n. E power j I can write as cos omega n plus j sine omega n. Fine. So this you can write as an cos omega n plus j a power n sine omega n. This is what a real part of x of n. This is what imaginary part of x of n. Yes or no? Yes. So how can we write real part is an cos omega n. So first thing is it is cos, that is multiplied by a. So let us assume a varies from 0 to 1. When a varies from 0 to 1, what happens? It is decaying exponential. So when you multiply cos with a decaying exponential, what will happen? Cos will also decrease. That's what we have studied in continuous. The same logic you use. If you have any doubt, please refer my video on complex exponential in continuous domain. So it will be in different color. So decaying cos. So initially the cos will be like this. Fine. And what happens next? Next it will go decaying. Right. So this will be like that. It will go. So next it will be like this. Now we hope you remember this diagram. Right. So this will be gradually decaying exponential. Right. So this is what xr of n. Right, real part an into cos omega n, right? Similarly, for a is greater than 1, sorry, first I draw xi of n, it is decaying sine multiplied by a power n, where a is decaying. So how can we draw this? We can draw like sine initially 0, then we have a signal like this. Fine. So first it will be like this, then what will happen? Then it will decay. Fine. Right, so if you draw, it will be decaying sine. Right, like that it will decay. So this is xi of n, decaying signal, decaying sinusoid. Fine, so decreasing. In continuous, we can say decay. Here we will say decrease. So decreasing sinusoid. Similarly, we can draw for a is greater than 1 also. Right, so follow the same procedure I explained in continuous time signal. We will have a exponential discrete time signal. So next signal we are going to see is rectangular sequence. Like we have a continuous rectangular signal. Here we have rectangular sequence. Sequence is nothing but in discrete domain the signal is called sequence. Sequence is nothing but discrete signal. Right? So it is not continuous, so we don't use signal, but you can use interchangeably. You can use signal sequence. Sequence is specifically used for discrete signal, right? Because it is having a finite number, so we call this is a sequence. But you can use signal also, no issue. So what is the definition for rectangular signal in discrete domain is rectangular n, that is equal to 1 when n varies from minus n to plus n, 0 when n is greater than n. So what is the meaning? When n varies from minus n to plus n. This is what this meaning, right? So how can we draw when n varies from minus n to plus n? Let us assume this is minus n, this is plus n. So okay, this is 0, 1, 2, 3, and it is going. This is minus 1, minus 2, and it is going. So when n varies from minus n to plus n, the signal has a value of 1, right? So it has value 1. When n is equal to 0, 1. When n is equal to 1, 1, 2, 1, 3, 1. Up to when n is equal to n, it will be having value of 1. Similarly, when n is equal to minus 1, 1. When n is equal to minus 2, 1. Up to minus n also it is having a value of 1. It's like our, you see our discrete continuous time rectangular pulse. That's what it is known as a unit rectangular. Because why it is unit? The magnitude is 1. So That's all about basic discrete domain signal. If you have any doubt, please ask me in comment section. Thank you.